All right. Hello, everyone. My name is Blue and I want to first thank all of the wonderful HotMobile staff, volunteers, reviewers for their time and efforts, as well as the opportunity to present. So today I'll be presenting a Headworn Displays order picking project from Georgia Tech. Those that also contributed to making the project a success include Themoy, John Devansh, Pramod, and Dr. Thad Starner. So without further ado, here we have a preview or non-live demo of a user study comparing a range of Headworn display device designs and Headworn display devices during an order picking task. So order picking is the task of retrieving products from storage or buffer areas, so often in a warehouse, in response to a specific customer's request. So it requires an order picker to alternate their attention between location instructions and manipulating physical objects. So in our study, the location instructions are provided on a Headworn display, as shown here. We have a preview of all three devices we used in the study, but more details coming later. For now, let's first answer the questions, why compare Headworn display designs and why use order picking to examine Headworn display designs? So first, Headworn displays are considered for a wide range of uses, including order picking in warehouses, flying, inspections, operations, etc. In addition, many studies have compared Headworn display designs to current industry standards in these wide ranges of uses and found them as better alternatives as well. But little work has really been done to compare Headworn display models to inform trade-offs for future Headworn display designs. Secondly, we chose order picking as the task to evaluate Headworn display designs because it is one of the most successful current uses of Headworn displays, and an extensive body of work on Headworn displays has centered around order picking. Furthermore, the dual task nature of order picking with a Headworn display is representative of a whole scope of task guidance applications. Thus, by comparing Headworn displays to each other in a common task guidance scenario, we hope to provide Headworn display designers insight on the issues that might hinder the uses of these devices. So as mentioned previously, much order picking work has centered around comparing Headworn displays to industry standards. In most cases, the industry standard are pay-per-pick lists. And in almost all of these studies, the Headworn display has shown to have a faster pick speed, better accuracy, and lower perceived workloads than paper. Previous work has also exposed some characteristics of Headworn displays, such as display positioning, interface types, optical resolution, etc., that can influence user performance and comfort. So for example, researchers have shown that the weight of a Headworn display may result in stress and strain on the head and the neck. Now, although the current literature provides valuable insight on many devices individually, little work has done to examine the impact of hardware design choices from a more holistic perspective. So these existing gaps motivated our current study. So we chose three very different Headworn displays to compare to the control. So once again, the industry standard, the pay-per-pick list, during order picking to tease out their performances. So the three devices chosen from the study, from the left to the right, is the Google Glass Explorer Edition, the Magic Leap 1, and the Microsoft HoloLens. Not only are these devices the most popular in terms of sales and recommended use in the industry, they are also considerably different. So in terms of their resolutions, weight, ocularities, field of views, frame rates, and even their physically worn configurations. So some characteristics specifically of note that pertain to this experiment especially is that Google Glass has the lowest resolution of them all, as well as weight. HoloLens is the heaviest Headworn display with almost 15 times the weight of the Google Glass bearing down on the head. Only Google Glass is monocular, so that means it is only over one eye and also positioned above line of sight, while the other two's interface are in both eyes, seen with both eyes, and are in line of sight. Finally, the last thing of note is that the Magic Leap has a crossbody shoulder pack. Um, so while the other two devices are completely head worn, the Magic Leap 1 divides its total 661 grams, which actually makes it the heaviest device, total weight wise, but splits it almost halfway across the body. So only about 300 grams ends up on the head and worn on the head. For our experiment setup, we imitated a warehouse. So our warehouse consists of 7 bookshelves labeled A through G, seen on the left here. Each bookshelf then consists of 5 rows, 3 columns of 5 books each. So the top books of each stack represents the package or book that needed to be picked. All the others served as padding. So a user might pick the top package and then put it on the ground beneath on the bottom of the bookcase to indicate that they had picked a package in the study. Here we have pictures of the environment and how location instructions might have been displayed on a Headworn display. So following best practices from previous order picking studies, our interfaces were 2D screen locked user interfaces. Every Headworn display had the same interface look, but were standardized and proportional, yet scaled to each device. So what that means is the interface on the HoloLens might look bigger than the one on the Google Glass because the field of view is larger. However, it was proportionally taking up the same amount of screen real estate. So in the middle column here, the top view is called environment view. So the highlighted box represents the shelf and column that the package is in. In this case, the package is at shelf A and the leftmost column when the user is facing the bookshelf. Below it is environment view. So the highlighted box represents column and row that the package is in. In this case, the package is in column 2 and row 3. In case a user also wishes to confirm their pick, they have the package title and information on the left. Users can toggle between these views to locate their package. Let's get to some fun stuff. Here's how order picking looks like in action. So on the left here, we have John representing a user picking while wearing the Google Glass. So his view on the Google Glass is also shown on the top right here. Minor caveat, Google Glass was the only device we were kind of unable to screen record both the application and the camera at the same time. Thus, we created an overlay and also put a black background on the application itself so that interface is clear for the audience today. But usually during the experiment, the interface would be clear and transparent. So below that, we also have him putting on the glass to show all the wearable components. They wear very similar to regular eyeglasses. However, the interface is only over one eye, in this case, the right eye, with this little tiny clear piece here. So beside that picture, we do have an example of what the interface actually looks like on the Google Glass. Then here we have Devansh representing user picking on the Magic Leap 1. So as you can see, there are a little bit more components with the Magic Leap. For equipping the Magic Leap, he must first put on the shoulder pack and then the headset. And he also chose to wear the shoulder pack, which is also the processor on his hip. Then we have Thamoy on the HoloLens. So the whole headpiece is placed on the head. Most of the weight is on the nose bridge, but the device is secured by tightening the band around the head. And this wears similarly to the Google Glass. Everything is head worn and there's no additional configurations. Finally, our industry standard paper. So modeling current warehouse pick lists. All picks are given at once. So we separated location information very similarly to Headworn display interfaces. So shelf letter, shelf column, and then row. And in our case, you were able to see all 10 books or packages of one pick path at once. Now let's talk about actual study procedures. So our methodology is summarized as a 12 participant within subject user study. So we compared speed, accuracy, subjective workloads, and preference on devices while performing order picking. The devices, once again, were Microsoft HoloLens, Magic Leap 1, and Google Glass Explorer Edition. And we pit them against the industry standard of a paper-based pick list. Each participant would pick a total of 10 books off of a pick path before resting. They would then do 5 pick paths per condition. So we counterbalance pick paths with a 4x4 balanced Latin square to avoid order effects and learning effects. But to further diminish learning effects, we also had our participants trade up to an expertise order picking level before our experiment. Thus, for the entirety of our study, each participant would do a total of 2 phases, a training and a testing for conditions, 5 pick paths per condition, 10 books per pick path for a total of 400 total picks. So we worked them. Our a priori hypothesis was then that our users, like those from previous order picking studies, in their performance on Headworn displays would at least outperform paper, even if they might differ in extent. You might ask, how did we determine that our order pickers reached an expert level of picking? From pilot studies, we determined that around the 12th to 15th pick pack mark, users' learning curve started to plateau. Thus, for our experiment, we decided to have users do 20 pick paths prior to the actual testing portion of our experiment to reduce learning effects. So this is a graph of actual study data, averaging across all participants and their average time per pick path. So we see that 15 pick paths of training were on average basically sufficient for all users to reach a level of picking regardless of their prior picking experience. So pickers did not display significant learning after the learning curves plateaued, and this kind of reassured us that the training paths were sufficient to start extinguishing learning effects. The solid black line here, device training and testing. So we measured performance via the speed was from average time per pick path on device. Accuracy was number of errors during a testing condition. We also did a NASA TLX subjective workload survey between each condition, as well as a post-study preference questionnaire. So the NASA TLX survey tested mental subjective workloads, physical workloads, temporal workloads, effort, perceived performance, and frustration. The preference questionnaire tested overall preference, subjective accuracy, subjective speed, comfort, and learnability. After conducting a one-tailed t-test with Benjamini-Hochberg correction for multiple hypotheses on all conditions in terms of speed, we were surprised to find that only order picking on Google Glass was significantly faster than paper. So this is contrary to our hypothesis. However, on average, all 3 devices, they were faster, with Magic Leap 1 only 3 seconds slower compared to paper than Google Glass. Compared to paper on average, HoloLens, however, was a distant 3rd place. In terms of accuracy, on the other hand, we were once again surprised that only order picking on the HoloLens showed significantly less errors than paper, with an average of 3.2 errors less than paper, while Google Glass and HoloLens were roughly equivalent. For our subjective workload survey and preference survey, Google Glass had a significantly less temporal workload than paper, meaning participants felt less rushed while order picking, while both Magic Leap 1 and HoloLens were ranked as significantly less comfortable than paper. We did do a post hoc analysis to compare the devices to each other, and we found that both Magic Leap 1 and Google Glass were significantly faster than the HoloLens, while both HoloLens and Magic Leap 1 were less comfortable than Google Glass. So what could these results imply for Headworn display design? Number one, let's talk about comfort. Wearing a Headworn display for an extended period of time to perform any task requires that the display be comfortable. So our results showed that Magic Leap 1 and HoloLens were significantly less comfortable than paper in our post hoc analysis, so that they were less comfortable than the Google Glass. From our participant interviews, likely culprits included having to wear additional hardware on the Magic Leap because it was restrictive or felt heavy. Many participants also did not know where to put the processor. The recommended method is to put the shoulder pack in your pocket, but some participants did not have them. And thus the pack would just be left hanging, and while they're moving, would run into their leg. On the other hand, HoloLens was often cited as too heavy, especially on their nose bridge. So all of the HoloLens weight is worn on the head, and many felt the 600 grams weighing down on their face and neck. In addition, many also complained about a slow frame rate, which could also be attributed to an obvious color separation on the HoloLens interface. So this effect is due to sequential rendering of 4 colors on the HoloLens, which may result in color separation during fast movements, which may have caused them to feel dizzy or disoriented. Interestingly enough, though, the Google Glass also is color sequential at the same effective refresh rate. However, none of our participants mentioned similar woes about the glass. So maybe the smaller field of view made it less noticeable. In terms of speed, only Glass showed benefits. Users cited that they felt more focused from the small field of view, as well as the interface being a little bit above line of sight. So the interface designs here could have provided less distraction during their task. Whereas on the HoloLens, the interface was not only large to accommodate its larger field of view, but also in line of sight. So users might have had a harder time switching context between the real world and their interface instructions. Also, as an example of one design that might affect 2 design criteria, Magic Leap's shoulder pack was also not only cited as uncomfortable and restrictive towards movement, but also got in the way when users wanted to pick faster. So while they were trying to move faster, users would feel like their lower bodies were being bound by crossbody wires and weight. So while HoloLens performance in terms of speed and comfort were not the best out of all of the Headworn displays, only HoloLens was significantly more accurate than paper. While a larger field of view in line of sight interface could have detracted from timeliness, users did cite spending more time looking at the interface, which could have improved their accuracy in picks. So to sum up, we recommend future Headworn display designs to consider how different hardware characteristics such as impact weight on the head and body, motion artifacts, additional hardware, field of view, and display position, and how they might affect a user's ability to perform a task, especially in cases where trade-offs might have to be made, such as in the case of time versus accuracy for field of view and display positioning. As a recap, so only HoloLens performed better than paper in terms of accuracy, while being the heaviest device as well as the one with the largest field of view. Google Glass was the only Headworn display that performed better than paper in terms of speed and perceived temporal workload. Glass was also the lightest of the devices and the only monocular device, although the ocularity was not mentioned by participants during interviews. Based on our results, we do provide some design considerations for time, accuracy, and comfort. So future work can expand upon hardware designs with the introduction of more diverse hardware displays, Headworn displays in industry, as well as dive into like a myriad of different task paradigms for Headworn displays. So this concludes our presentation.